Okay, there's another kind of potential energy that looks a lot like this one. So what is it? Different kind of system interacting with a different fundamental force. So let's go back to fundamental forces. Gravitational force was one of them. What's another? Electric force. Okay. So we had the gravitational force was negative g m1 m2 over the magnitude of r squared r hat. We had the electric force was equal to, between two charged objects, a very odd looking constant, 1 over 4 pi epsilon 0, times the charge of one object times the charge of another object over the distance squared r hat. And the difference with this, one of the big differences between this force and the gravitational force was, so the similarities are, we have this 1 over r squared here, right? So 1 over distance squared. We have some property of each object. The distances, though, is not necessarily attractive. Gravitational forces are always attractive, but we can have, so if we have a positive charge and a negative charge, they do indeed attract each other, and the magnitudes of those forces better be the same. But what if we have two positive charges or two negative charges? Yeah, they repel, don't they? So we get So we know that in the case of gravitational potential energy, that's gravitational force is attractive. The gravitational potential energy goes like 1 over r and it's negative. So it's reasonable to think that probably for this case it's going to look the same. But for these two cases, maybe not, huh? It might look different. So we go through the same kind of, it's in the book and I'm not going to derive it here, but we go through the same kind of argument we went through to get this gravitational potential energy for this force. And we find that the electric potential energy ends up being, we've got the 1 over 4 pi epsilon 0. We have the charge of object 1, we have the charge of object 2, we have the distance between them, which we can also just write as an undecorated r, the magnitude of r. And it turns out we don't need the minus sign to get it to work out right. Why don't we need the minus sign? Yeah. So this needs to be, so if we have a proton and electron, we want the potential energy curve to come out to look the same as it did for a gravitational potential energy. So now we want U electric for plus and minus charges. So this expression needs to be negative, is it? It is, isn't it? Because this is, this is the electron, it has a negative charge, and if that's, so we've got a negative sign, so it's going to come out negative. What's going to happen if they're both positive, though? Yeah, they're going to repel. They definitely repel. And so what's the potential energy curve going to look like? So we're just going to flip it, right? So it's going to look like, this is now the electric potential energy for two positive charges or two negative charges, right? Because if these are both negative, we're going to get a positive number. If they're both positive, we're going to get a positive number. So that, all right. So we should be able to do problems involving electric potential energy. So let's record this result over here so we can use it. U electric is 1 over 4 pi epsilon 0 Q1 Q2 over R. No minus sign. So let's do a problem involving a simple problem. Let's say we've got 2 electrons, and we start out with them far away from each other, heading toward each other, and they have the same speed. So 2 electrons far apart, initially far apart, each with speed v approaching each other. How close do they get? So first we're going to draw a diagram. And because the energy principle has this E final, E initial thing, when we're doing an energy problem, it's a good idea to draw a little picture of the initial state and a little picture of the thing you picked as the final state, just to remind you. They don't have to be very sophisticated. So here's our initial state. Call it. Now, how far do they get? How close do they get? What does that say about the final state? They're repelling each other, so what's happening is they're coming together, they're slowing down. It's implying that they stop and maybe turn around and go the other way. Okay, so looks like the final state we want then is when there's some final distance, our final, right? So we had to kind of, from the problem statement, we had to kind of figure out what the final state we want was, right? Okay, so guess we start by writing the energy principle because we've got 2 positions. So we're going to write E final is E initial plus work, and now we have to pick a system. So what are we going to pick? Yeah, it's nice to pick them both because then we don't have to worry about. So system, 2 electrons, and therefore we can do this all in outer space where nothing is interacting with it. In fact, these electric forces are so strong and these particles can be moving so fast that the Earth, even if it is on the Earth, it doesn't have a chance to do very much work. So approximately 0. So what do we need in here? Oh, what terms do we? So initial energies, what terms do we need? Initial kinetic energy of electron 1. Initial kinetic energy of electron 2. And they're interacting, aren't they? So we need the electric potential energy. And we could write the rest energies, and it's fine to do it, but are the rest energies going to change in this problem? No, so we can just leave them out. And what goes over here? Well, we'll put down all the terms that are relevant. So K1 final plus K2 final plus U electric final. Okay. So what's the next step? We want to identify all the terms that are 0. So let's, in this case, which ones do we have to keep? Which ones are not 0? Yeah. Oh, so okay, that's a good question. So the question is, because it's an elementary particle, it's a small particle that could actually be speeded up till it's going close to the speed of light, would you need to use the relativistically correct form of kinetic energy? The answer is that it's certainly correct to do that, but it's okay to, in the absence of information in the problem statement saying that they're going really fast, it's okay to assume that they're not. So in this problem, you would be given initial speeds, and once you're given an initial speed, if you see that it's 2 times 10 to the 6 meters per second, you say, well, I don't have to worry. And if it's 2 times 10 to the 8th, you say, I better worry. Okay? So here again, we're talking about the structure of the solution, not the details of grinding through numerical calculations. So this is really far apart. Well, there's considerable convergence. Look like 6. So you're saying the initial kinetic energies of the 2 electrons and the final electric potential energy are non-zero, which means the other things are zeros. So why do we think this is 0? Really far apart. So therefore this is a really big number and R is big. Okay, good. And these are 0 because we're assuming they come to some distance, they stop. We want the point where they stop. Good. Okay. So now we've actually got an equation that says the final electric potential energy is equal to the sum of the initial kinetic energies. And now the final question is, where's Waldo? So where's the unknown? Are we going to be able to get out of this what we want? How close do they get? Yes, that's exactly right. So this distance of closest approach is hiding in here, isn't it? It's this R.